to talk about element or trace element bioimaging at micro and nanoscale. And so my lecture here is I will give an introduction into imaging in general, and elemental imaging techniques. So imaging in analytical science and element imaging techniques. Then I will focus on the secondary ion mass spectrometry as a technique. And then the nanoscale secondary ion mass spectrometry, the NanoSIMS. I will explain this technique, how it works, what are the possibilities, the challenges and drawbacks, and also then the challenges for sample preparation. This is a special chapter now here in my presentation, because sample preparation is very important for these techniques, and it can be very complicated, sample preparation. Therefore, we have to talk about sample preparation. And after that, I will show you some applications from our lab, or from our projects of NanoSIMS, and complementary techniques for correlative imaging. So I will not only talk about NanoSIMS, but also a little bit about other techniques which we can apply in parallel to do these elemental bioimaging. So the basic question is, why do we like imaging? And maybe you know this word in English, a picture is worth 1,000 words. And it's true. Here I have a photo, a picture of the city of Po, where I'm living now. So they have an impression where I'm now situated here. And with an image, I can tell you much more about the beauty of this city than with 1,000 words. So I could describe a lot, but an image gives you immediately a lot of information about how it's here, the city. And another, what is also true about imaging now is very popular. With everybody has now with his telephone also a small photo camera and can pictures everywhere. Everyone is doing pictures and videos even everywhere. But it's not only nowadays that imaging is very popular. It was already in the past, because we can say an image shows more than 10,000 data. And already in the past, since the dawn of man, information was given by images, by visualization, because it is possible, like here, these cave paintings in the past, because with these images, you can transmit a lot of information at the same time. And it's possible with an image to absorb a large amount of data in the same time. You can communicate both abstract and concrete information. I will give you an example how data and images are related. For example, here the measurement of relative light intensities, a presentation as a data in a matrix. You see here these data, these abstract data, and I suppose it will not tell you a lot what is behind, what kind of information is behind. Of course, it is the value of each of a pixel in an image, and we could transform these in shades of gray in an image. And now you see more or less 9 data points. But I suppose also these 9 data points doesn't tell you a lot what kind of information is behind. Maybe you know already, maybe not. But I will show you now that 9 data points, it doesn't tell you a lot, but I would say 100,000 data points give you the whole information. So which shows you that absorbing large amount of data in an image is even more easy than a small amount of data. So what do we see here? In fact, it is this mister here. And now we see the whole picture. And I think with 100,000 pixels, you can absorb the whole information. So with images, it allows us to absorb quickly the whole information. And also images are used as proofs, or as proof in science. An example here, the image of the so-called COVID virus or SARS-CoV-2 virus. And this was one of the first images of these virus obtained with transmission electron microscopy and these images are colorized. So by these images, we had worldwide the first information. It was done in a laboratory in the US, about the first information about how it looks, these coronavirus. And finally, these scientific images gave an example for a lot of popular images of the coronavirus, like this image here, which of course these are artificial images, or these kind of images of the coronavirus. But behind there was the first were these scientific images from electron microscopy. So images and analytical science are somehow related. But as I told you at the beginning, an image is more than 10,000 data. Also, an image is more than the visual impression. It is more than only seeing an image. For example, here already an example from NanoSIMS. It's a calcium distribution in algae cells, analyzed with NanoSIMS. We can do present it here as a grayscale. We can also present these in a color scale. So different representations of an image are possible, but it gives you different visual impressions. Of course, both impressions is only a visual impression, if it's color or grayscale. But we should not forget, behind each image is a matrix of analytical data. Images and analytical science are somehow related if we look on the matrix of analytical data behind. And I would say also, an image is more than a visual impression. Don't forget the data behind. So it's a matrix of data to be treated and interpreted. There are raw data, for example, measured intensities, or treated data, normalized intensities, intensity ratios, isotope ratios. For example, here, in such an image from NanoSIMS of 256 times 256 pixels, there are more than 65,000 data points. And if you look here in only a very small area in this image, you have the raw data, the measured intensities, but you can also make normalization or ratios inside. So there are a lot of data to be treated in such an image. So in general, raw data can be obtained from detection of photons, for example, visible light, UV, X-rays, electrons, atomic and molecular ions in mass spectrometry. Later, I will focus on these atomic ions in mass spectrometry. Coming now to elemental imaging, and elemental imaging or elemental bioimaging, that means imaging of tissues and cells. This can be an important contribution to the investigation of biochemical functions, biosorptions, and bioaccumulation processes at cellular and subcellular level. And I will give you, for the moment, only 4 examples how these can be done. In general, it's scanning the sample surface with a high energy beam, photons, ions, or electrons, and then the detection. So here, 4 examples simply. I think all of you may know these examples: laser ablation coupled to inductively coupled plasma mass spectrometry, ACPMS. They use photons, and you are scanning the sample surface. In secondary ion mass spectrometry, we will talk about this later, there are ions used for scanning the surface. In X-ray fluorescence or synchrotron-based X-ray fluorescence, there are photons used. And in electron microscopy, I already mentioned that we are using electrons. They are either used for scanning, there are scanning techniques, or also simply the transmission of the sample. So in this case here, in the first case, we detect atomic ions. And in the second case, we detect characteristic X-ray. And when I talk about this transmission electron microscopy, I talk about this XEDS detector for characteristic X-ray in the microscopic image created by the electrons. So only 4 examples, but imaging techniques and also element-specific imaging techniques are not limited to these 4 examples. There can be much more. For example, there are a lot of combinations and also techniques possible simply by combining microscopy or imaging with element or molecule-specific techniques, like, for example, bulk techniques like ICP techniques. And in the middle, there are a lot of techniques possible. I cannot talk about all these techniques, but only simply a few examples. We are already talking about laser ablation ICPMS. We are talking about scanning transmission electron microscopy with an EDS or XEDS detector. And in this scheme, we can distinguish two areas. An area where we have a high resolution of the image, but normally lower sensitivity for the element-specific signal. So STEM EDS has a very high resolution, but the sensitivity is more or less on the percentage range for element-specific signals. Then we have here techniques like laser ablation ICPMS. We have a lower resolution. It's more better to only analyze the tissue, not the single cells, but we have a very high sensitivity for the element-specific signal. And there are techniques I would like to focus today. There's a NanoSIMS, but also synchrotron X-ray fluorescence, but NanoSIMS, it's somehow in between, give you already good resolution and a good sensitivity, but not the sensitivity is not as good as, for example, laser ablation, and the resolution is not as good as electron microscopy, but it combines element-specific signal and resolution in an optimal way, and we will see later what we can obtain with this NanoSIMS technique. So I will talk about NanoSIMS, but also about, I will talk later a little bit about synchrotron XRF, which gives similar resolution depending on the beam line. I also will talk later, when we are talking about correlative techniques and other techniques, about TM, ICP techniques, and also XAS for speciation analysis. So to talk about the resolution again, to situate a little bit the NanoSIMS technique between human eye electron microscopy and light microscopy, then there is the NanoSIM has a resolution, spatial resolution of an image. Yeah, not as good as electron microscopy, but in the same area, in the low resolution area of electron microscopy. So it is in the area of cells and bacteria, we can say. So I was already talking a lot about secondary mass spectrometry now, and now I will talk a little bit more what is behind this technique. We have, first of all, a primary ion beam. The primary ion beam is hitting here a sample surface. The primary ions have an impact in the sample surface. There's a sputtering process, and the sputtering process creates atoms, clusters, and a part of these atoms and clusters are ionized, and these are the secondary ions which are extracted with an extraction lens and then sent to the mass spectrometer. Only these secondary ions are finally analyzed. And what we can do by that, we can do simply record a mass spectrum of the atomic ions and the cluster ions. We can do isotopic measurements, isotopic ratio measurements. We can do a depth profiling by bombarding a surface always on the same spot. We can go deeper and deeper in the material and have a kind of depth profiling. And we can scan the surface and have an image. So we are in imaging. And even we can combine depth profiling and imaging, and we can have access to three-dimensional images in a specific range, but we can create three-dimensional images. So I have to also to talk, because we have a little bit of time today in this webinar, about the difference between static and dynamic SIMS. Because a SIMS is not always SIMS. There are two principal different techniques, the static and dynamic SIMS. Static SIMS means that we have primary ions, usually with a lower energy, a pulsed primary ion beam, and the secondary ions are only ejected from the topmost atomic layer here. And because of the lower energy, the secondary ions can be atomic but also molecular ions. And by these also molecules can be detected, but only from the topmost atomic layer. And this technique is, for example, time-of-flight mass spectrometry with SIMS, or the so-called TOF-SIMS. This is a static SIMS technique. And today I will focus later on the dynamic SIMS, where the NanoSIMS belongs to. In the dynamic SIMS, we have a high-energy primary ion beam, high-density primary ion beam. The secondary ions are formed not only from the topmost atomic layer, but from a few nanometers of the sample surface, up to 10, 20 nanometers of the sample surface. And because of the high energy and the continuous beam, we are creating only atoms and small clusters, but not molecular ions, only ions from atoms and small clusters. These are the dynamic SIMS technique. And let me now focus mainly on the dynamic SIMS technique and what is going on during this ionization process in dynamic SIMS. So here we have the primary ions. They are hitting the sample surface, and we have a cascade of collisions. These neutral atoms, clusters, electrons, and secondary ions are created. Only the secondary ions are later then used for analysis. Everything is done under ultra-high vacuum. This is later important when we are talking about sample preparation. And the bombardment is with focused primary ions. We have this collision cascade, and it's 10 to 20 nanometers depth. So not only the topmost layer, it is going in depth in the material. All molecules are broken, so we have only single neutral atoms or clusters or electrons. The small fraction is ionized, and the secondary ions are available for mass spectrometry. And the secondary ions are characteristic for the local composition. They are collected and separated in a magnetic sector analyzer according to their mass-to-charge ratio. And SIMS reveals dynamic SIMS elemental, also hydrogen included, and isotopic surface composition. So we can have an elemental information, but also an isotopic information. And the consequence is that the samples must be stable in ultra-high vacuum and must be flat. We will come back later to this point during sample preparation techniques. And a little bit of history of SIMS or dynamic SIMS instruments. They were mainly developed by the Société Chimica. It's a French company, starting in the 60s with their first instrument, developing a dynamic SIMS instrument. And there were different instruments developed during the last decades. And then already 20 years ago, the first NanoSIMS came on the market, which of course also still had some evolution until today, the most modern instrument of this type. And the evolution of all these techniques, we can also see these here when we look on the beam size of the ion probe or the ion beam. In the 70s, it was a diameter of 2 to 3 micrometers. And then by the 80s, 90s to the year 2000, and the NanoSIMS now has a beam diameter of 50 nanometers, so from 3 micrometers to 50 nanometers in more or less 30 years. And this also gives you then an idea of the best available resolution of an image. So with NanoSIMS, we can go down to 50 nanometers resolution in the image. There's a physical limit. You may ask, can we go even more down and down in this evolution? There's a physical limit. It's calculated by physicists. I cannot give you a detailed explanation of that, but it's related to the sputtering process and the energies. The physical limit is around 12 nanometers. Physicists say you cannot go lower than 12 nanometers in SIMS. So with 50 nanometers, we are already quite down to the best resolution in SIMS. So this is in our laboratory in Pau in France, our NanoSIMS, just in a new building, in a new laboratory since 1 year. So now you have here an impression of these NanoSIMS. It's part of the mass spectrometry center at our institute in Pau in France. And you can understand the NanoSIMS as a scanning ion microprobe with a multi-collection mass spectrometer. So you have here a sample. First, you can observe your sample with a CCD camera, and then put to have an overview about your sample. CCD camera is like a microscope with an optical microscope, and then you put your sample in front of the ion beam, and you use a primary ion beam, either cesium plus or oxygen minus ions. And I come later to that why cesium or oxygen. And with these, either cesium or oxygen, you are scanning the sample surface down to 50 nanometers resolution. And then you are ejecting or creating the secondary ions, a secondary ion beam, which is extracted, focused, and then separated in a mass analyzer. And then we have 7 different detectors. And with each detector, you can create an image of a specific ion or a specific mass, specific chemical element. Here it's carbon, oxygen, nitrogen, sulfur, phosphorus, arsenic, selenium. And already you see here nitrogen and phosphorus are not detected directly on the atomic ion, but on cluster ions. This is an example from one of our projects, an arsenic project. I will come to this, we'll present this project in detail later, but let's have a look here on this arsenic signal, this arsenic image. Usually what we have, when we have a quite low intensity, we can do one scan after another. So we are not limited to one scan. We can do 10, 20, 30 scans, even more, and then summarize all the intensities. After a drift correction, we can accumulate the intensities to have a, you see here, a brighter or more intense image. This is we are doing usually that, especially if and we want to look to trace elements which are low concentrated in the samples. So coming now to the question why oxygen and cesium primary ions, oxygen minus or cesium plus, why these are used. With the cesium primary ion beam, we can create secondary ions here on the left side of the periodic table, so more or less the non-metals. So these are NanoSIMS applications, cell imaging of carbon, nitrogen, oxygen, sulfur, all these major elements in biological tissues and cells. You can create secondary ions of these with the cesium plus primary ion beam. And with the oxygen primary ion beam, oxygen minus, we have access to the left side of the periodic table. It means more or less all the metals, trace metals. There are some elements, of course, here in the middle, where you can use both ion beams to create secondary ions, but not with the same sensitivity. So with both ion beams, we have access to almost all chemical elements. And why cesium and oxygen? Because they have the largest distance or largest difference in their electronegativity. Therefore, cesium and oxygen is used here as elements for the ion beams. So how such an ion source is made of, or here's an example of the cesium plus primary ion source. So it's quite easy. There's a reservoir of cesium carbonate, which is heated to create a cesium vapor. And then this cesium vapor is ionized, and the ion beam is extracted. And so we have a cesium plus ion beam. And such a cesium ion source, this cesium carbonate reservoir, lasts for more or less 1 year of operation, and then it has to be replaced, because then the cesium carbonate is, everything is used. The oxygen ion source is a little bit more complicated to create oxygen ions. The classical ion source used in SIMS was the so-called duoplasmatron primary ion source. I will not spend too much time on that. It's a plasma created here, creating these oxygen ions. But these ion sources have a low beam density, low lateral solution, so you cannot go down to 50, but only 200, 300 nanometers. And what is also important is the long-term stability is not very good. Really frequent maintenance and cleaning is necessary when using these ion sources. This was the reason to replace these ion sources with a new concept. And we did this together with the Kamika, the constructor of the NanoSIMS, to fit a new type of ion source, which was constructed by Oregon Physics in the US. They developed this ion source, but we fitted this ion source to the NanoSIMS. And it's a radio frequency primary ion source. It's working completely different than the older ion source. It has here an upper plasma region. It is working, in fact, those who are familiar with ICPMS, it's like an ICP, but not of argon, but of oxygen, and not lead hot, not less an argon plasma and ICPMS. It is an oxygen plasma temperature of 400 degrees, more or less, but this is sufficient to create here oxygen ions and plus ions in this area, also electrons and a little bit of oxygen minus ions. But we want to have these oxygen minus ions, and therefore in this lower plasma region, with this magnetic filter, the O minus ions are concentrated and then extracted and create this ion beam. This is a really high density ion beam, and high density ion beam means better sensitivity for trace metals or for metals in general, because you have a higher energy. We can also by this achieve a higher lateral resolution, and even we could achieve here 40 nanometers better than the 50 nanometers of the cesium ion source. So sharper images, and also what is very important, very long-term stability. Less maintenance is necessary for this type of ion source. In our laboratory, we were the first laboratory had these ion source, or this kind of prototype of the ion source worldwide. Now it's commercialized, and a lot of NanoSIMS lab are meanwhile also equipped with these new ion source. So this is the scheme of the NanoSIMS. Again, here we have here the ion sources, the oxygen ion source, the cesium ion source, the primary ion beam, hitting here the sample, scanning the sample surface. The secondary ions are extracted, focused with many, many lenses here. It's quite complex instrument, in fact, and then sent to the mass analyzer, separated according to their mass to charge ratio. And then we have here 7 detectors, 1 fixed and fixed movable detectors to select the masses we want to analyze. And we replaced here these duoplasma ion source by these radio frequency plasma primary ion source, and to achieve really high resolution images of trace elements. And I can give you here a first example. These are calcium, iron, copper, manganese in a chloroplast. So they are essential trace elements, metals in a chloroplast of a plant. So what we see here is not only a cell, it is only the chloroplast of the cell. Here you see here the scale is 2 microns here. So we can really see in the chloroplast the essential trace elements essential for photosynthesis here on the subcellular level. And this was now possible with these new type of ion source, which we fitted to the instrument. So let me, at the end of this first part of my talk, summarize the characteristics of NanoSIMS. You can analyze or detect almost all elements from hydrogen, also the hydrogen isotope like deuterium, tritium, up to plutonium, but with different sensitivity. Parallel detection of 7 masses, 7 detectors is possible. High sensitivity. High sensitivity means in imaging ppm, not ppb here, but ppm in imaging. We can achieve a high resolution imaging down to 40 nanometers lateral resolution for subcellular imaging, 40 nanometers in case of the oxygen ion source. I was not talking in detail about the mass resolution, but we can also have a high mass resolution up to 9,000 for the separation of interferences. And I also was not talking about the transmission, but in comparison to other mass spectrometers, we have a quite high transmission of 80% of the created ions in the ion source or during the sputtering processes are later then also detected at the detectors. But of course, there are some drawbacks. The quantification is difficult because of matrix effects. So it is mainly qualitative analysis, what you do, qualitative images. We can, of course, compare in one sample the different intensities, but we cannot really quantify the elements in the sample because what you need matrix match standards which are homogeneous at the nanometer level, and this is quite difficult to achieve. And also sample preparation, especially for biological samples, is challenging. Sample preparation is challenging. Therefore, as I told you at the beginning, I will spend now a small chapter on sample preparation, how to do sample preparation for SIMS and especially for NanoSIMS and for biological samples. This general preparation scheme for samples for SIMS or NanoSIMS here is you can have soft material like cells or tissue. If we are talking now about the biological samples or hard materials, for example, eggshells, bones, we are already working on this kind of material. So if we have here, as an example here, a sample, and the sample is needs to be fixed, so it's a fixation and dehydration. Dehydration because we are working ultra high vacuum, so it must be dehydrated, the sample. Oops, sorry. And then the sample usually, not necessary, but usually we are doing a resin embedding of the sample. Then the sample can be cut in the middle. And then depending if it's a soft material like cells, tissue, we do an ultra microtome sectioning. We're doing very, very thin slices of 300 nanometers. And then we depose it on a wafer, silicon wafer, which is 5 to 5 millimeters, which fits well to our sample holder. But on this wafer, we have very small sections of the sample. If it's a hard material, like for example a bone, we are working on that. We are doing not an ultra microtome section, it's not possible for this hard material, but we use a micrometer wire saw for sectioning. And then the surface needs to be polished because we have to have a really very flat surface. And we need a gold coating. And why gold coating and also why these silicon wafers? Because we need a conductive surface for SIMS analysis, SIMS imaging. So what is the consequence? We do first of all a surface analysis. So the consequence is the fixation means that we have static information of a dynamic system. If it was before a cell or a tissue, of course it's a dynamic system, but we need to fix it. So we have static information of a dynamic system. And because of the surface analysis, we have only three-dimensional analysis of a two-dimensional analysis of a three-dimensional object. So these are, in fact, the limitations of this kind of imaging. We have two-dimensional analysis of a three-dimensional image object. Outgoing from this general preparation scheme, we can also do correlative imaging with other techniques. For example, this ultra microtome section is very well adapted also to do transmission electron microscopy after that. This is more or less the same sample preparation. When we do this kind of preparation and resin embedding, sectioning with a saw and then polishing and coating, you can also do, after the SIMS analysis, Laser Ablation ICPMS analysis for correlative imaging. And also what we already did, we did already microtomography, but then we have to do it before all the sample preparation procedure with the raw material. So how to do this now? This is an important point: is fixation and dihydration and resin embedding for biological samples, and why it's necessary. Because based on that, we need special sample preparation strategies of biological material for NanoSIMS. So again, I want to summarize, and really I spend a lot of time now about sample preparation because it's a really important point for this technique. NanoSIMS requires flat samples to avoid artifacts during the ionization. Dehydrated samples, I talked about these, because they have to be stable in ultra-high vacuum. And conductive sample surfaces to avoid charging effects from the ion beam. And how these requirements can be compatible with biological samples or biological cells or tissue. So we can adapt sample preparation methods from electron microscopy to NanoSIMS. So the general preparation scheme in electron microscopy is that we have a chemical fixation of the cells, like glutaraldehyde, formaldehyde, osmium tetroxide, dihydration with different solvent bath, acetone or ethanol, and then a resin embedding also with solvent bath with increasing resin concentrations. And finally, then we have a polymerization and a fixation of the biological material in resin. But what we usually prefer it's do everything on low temperature, so-called cryofixation, to avoid the chemical fixation, because the chemical fixation can alter more or modify more the structure than the cryofixation. If the cryofixation is done properly, it has to be done with a high pressure freezing of the tissue. So a very controlled freezing at 2000 bars during 20 milliseconds at a temperature of minus 150 degrees, more or less. And then in this way, we have a freezing of the sample without forming ice crystals. And by that, we have we are preserving the ultrastructure of the cell. So this is the cryofixation. But after that, we need a dehydration too. It can be done by cryosubstitution or lyophilization at low temperature, and then resin embedding with special resins also at low temperature. So everything is done at low temperature. Need special instruments for that. It can it's really specific equipment is needed for doing these cryofixation procedures. At the end, for both ways, it's the same. Ultra microtome to do sections for NanoSIMS, and it can be in parallel do sections for electron microscopy. So we are collaborating here with the Bordeaux Imaging Center, who have these techniques for cryofixation and cryo preparation techniques. And why do these cryofixation? Because when we want to look on trace metals, then we have less redistribution of the highly diffusible trace metals. With the chemical fixation, there's a risk that the trace metals which are not tightly bound, that they are washed out. But with cryofixation, we are limiting this risk. We are limiting this risk during the cryosubstitution, because the limitation of the NanoSIMS is that we cannot directly analyze frozen hydrated sample. This is not possible. There's still a small risk of redistribution of the metals, but the risk is smaller than doing the chemical fixation procedure. So again, NanoSIMS requires flat samples. When these sections are prepared with an ultra microtome, the thin sections, then we have flat samples. Dehydrated samples we achieve these by embedding these in epoxy resin. And the conductive sample surface we achieve by deposing the sample on a conductive silicon wafers. If the ultra thin sections are really smaller than 500 nanometers, then we have still conductivity. If not, there are thicker samples, or if there are thicker samples or not conductive sample surfaces, then we have to coat these with gold or platinum with a sputter coater. So now in the last part of my talk, I will give you now some examples of different studies, highlighting the potential of NanoSIMS and related techniques for element imaging in cells and tissue, what we have done in our laboratory. So 3 projects I want to present: barium sulfate nanoparticles in human lung cells, arsenic localization or speciation in brown algae cells, and if you have still a little bit of time, selenium mercury nanoparticles in whale liver. So the first project was the question how nanoparticles accumulate in human lung cells. It was a collaboration with a university in Germany with toxicologists and microbiologists. So, human lung cells were exposed to barium sulfate nanoparticles for 72 hours. And here's an example for the 0.2 milligram per milliliter barium sulfate exposure. And it was analyzed with both ion sources. First with this cesium ion source and then with the oxygen ion source of the same cell. And here we see with the carbon-nitrogen cluster, we see the nitrogen in the cell. With the nitrogen, we see more or less the cell structure because the nitrogen represents all the proteins. So we see with the nitrogen the whole cell structure. On the phosphorus signal, we see also the cell nucleus here inside of the cell and the nucleolus of the cell. And then, for example, with the sulfur, in this case, we do an overlay of the sulfur and the nitrogen. On the sulfur, we see the sulfate of the nanoparticles. So here we already see the small nanoparticles in the cell. We do the same with the oxygen source. It means the metal detection. With sodium, again, we can detect we can detect more or less the cell structure. And then, of course, we use the barium signal directly from the barium nanoparticles to detect the nanoparticles. And we see here smaller particles and also agglomeration of particles here. An overlay also give you then the situation of the nanoparticles in the cell. But what we observe too, when we see, first of all, the nanoparticles accumulate in the cytosol, but do not enter the cell nucleus. But if we put here logarithmic scale, then we see more of the barium, but of the barium around also of these small particles. So this gives us an indication, probably a part of the barium sulfate is already dissolved and distributed in the cell, or starting to distribute in the cell. But not all the barium sulfate particles apparently are stable. Although barium sulfate is known to be very unsuitable, but apparently as a nanoparticle, it starts to dissolve. However, we verified this with other cells. We didn't observe only one cell here. So this is an example of another cell. So with the oxygen source, we see here four small barium sulfate nanoparticles inside of the cell, not entering here the cell nucleus. But if we apply a logarithmic scale, we see suddenly that barium is distributed all over the cell and also in the cell nucleus. Apparently, the barium is partly dissolving and then distributing all over the cell, revealed by these by the logarithmic scale. We verified this with another example. We see the same, and then we could also do some calculations. So pixel by pixel, area by area, to see how much barium is still in the particle, to do a relation between the particle, barium with the particle and the barium dissolved in the cell. As I told you at the beginning, it's not only the visual impression, we can really treat the data pixel by pixel. And what we saw here, that rough quantification here is really only a relation to see inside of one cell, compare the different barium signals. So about 30 to 50% of the barium of the nanoparticles is dissolved. 3 to 7% is located still around the particles, but dissolved, and the majority is distributed in the entire cell. But there's here another problem. I told you at the beginning, we have here only, in fact, a static image of a dynamic system. dissolving of the nanoparticles inside of a living cell is also a dynamic process. But of course, doing the fixation, we have here a static image. The question is how to make a static image dynamic. And for that, I'm collaborating with a mathematician of the University of Frankfurt who's doing simulations. So on basing on imaging data, he can do simulations and can see how the dynamic could be behind when applying specific physical chemical rules. And he's applying non-linear diffusion equation, for example. Honestly, I cannot explain you in detail what he's doing, but he can do very interesting things. And as an example here, the first calculation to make, in fact, a static image dynamic, he was calculating the solution here of 4 nanoparticles inside of a cell. So this is a model here. So he created a small video and show with these equations how these particles are dissolving by time here, and the barium is distributed all over the cell. So this can be done by simulation, by mathematical simulations. Coming now to the next project, and this is more related to environment. The question is here how arsenic accumulates in the brown algae of Sargassum, a tropic algae. It's a national project with the different collaborators from Po and also from other institutes in France. And the question behind this, or the problem behind is that there is blooming and beaching of the brown algae Sargassum at Caribbean beaches. And it's more and more an ecological and economic disaster, because there are more and more of these Sargassum algae is on the beach, on these islands. And there's this French island, Guadeloupe and Martinique, these islands, and therefore we did this project. And these algae, the problem is they show a high arsenic accumulation, up to 35 milligram per kilogram. That means compared to the seawater, where there's a very low arsenic concentration, the concentration of about 10,000 times accumulation of arsenic. And we wanted to investigate with NanoSIMS and the stems and leaves by NanoSIMS, and the samples are from Guadeloupe. Here's an example from the sampling point from this island, and you see these huge amounts of algae beaching, deposed on the beach, and it looks not very nice, but it's also quite toxic behind because of the arsenic. So we had different sampling campaigns, and we always had samples directly from the sea. Then there is an area which we did not regard, and then what is called shore, and then the beach. In between the sea, where it's really the fresh algae, the shore is already partly decomposed, and the beach is decomposing already. The algae is dry and decomposed. So at these 3 areas, the samples were collected. So before, during, and after degradation. And then we were analyzing the leaves, the stems, and the floats of this algae by NanoSIMS. And what we see here, an example from the stem with the cesium source. So we see here the cell wall. In the cell wall, we see here the nitrogen, but also in the cell wall, we see a lot of sulfur. And what is important, the cell wall, but mainly the cell wall, is full of arsenic. It's the cell wall. It is inside of the cell. In some organelles, we see some arsenic, but the main arsenic concentration is in the cell wall, what we observed in this project. And it's colocalized with sulfur and also nitrogen and oxygen. But important is colocalized with sulfur. And the same is for the leaves. And here we see that the arsenic is mainly in the epidermis of the leaf. So this is also NanoSIMS image, arsenic NanoSIMS image of a leaf cell in the epidermis, but also on some organelles inside of the cell, but mainly again in the epidermis or in the cell wall. And colocalized, strongly colocalized with sulfur. And we did also correlative imaging of the Sargassum leaf cells. With, these are the NanoSIMS images with transmission electron microscopy with our colleagues from Bordeaux. And also we did some synchrotron experiments for see other elements like cobalt, iodine, copper, and calcium. You do not see directly the correlation, but it was the same cell which we analyzed here with 3 different techniques. And we only have to turn now the images, and then you see directly that we analyzed here the same cells. But what we want to do going further to do also speciation is XAS, with X-ray absorption at a synchrotron of these arsenic, X-ray absorption spectroscopy. I don't want to explain in detail how it works, so I think I don't have time for that, but we have these XANES and XF spectra, absorption spectra, and it's like a fingerprint for the species behind. And we did here linear combination. By linear combination, we can fit the spectra to the spectra of standards. So at the ALBA synchrotron in Barcelona, we analyzed the bulk sample. It's not a speciation inside of, it's not a spatial loose speciation. It is a bulk sample speciation. So here we analyze different standards, arsenic standards, arsenic with glutathione, arsenic sugar, arsenobetaine, arsenocholine, and also inorganic arsenic 3 and 5. And here the inorganic arsenic spectra, here the arsenic sulfur compound, so arsenic sulfur binding, and arsenic carbon bonds. And then we analyze the samples from the beach, the shore, and the sea, and the stem, leaf, and float. And then by fitting, we got a relative distribution of the species. And also we see modification or an evolution between sea, shore, and beach. And what we see here is that in the sea, here at there's also, these are the 3 samples, stem, leaves, and floats. We see more or less this similar distribution of 40% arsenic-free, 40% sulfur bond arsenic, and 20% carbon bond arsenic. In the shore, there's not a little bit decomposed, but not completely. We see the same, but in the beach, we have 59% carbon bond arsenic, including arsenic sugars, and 25% arsenic 5. So there is a kind of decomposing, maybe also due to bacterial effects, that we have a different arsenic species at the decomposed algae at the beach. We compared this with, we did HPLC ICPMS together with Veronique Wakina and Fabien Sebi here in Po. With HPLC ICPMS, I don't present the data here, but we got similar results. It was confirmed by HPLC ICPMS. So what are the summary of these observations and hypotheses? The fresh algae, stems, leaves, and float of the sea and the shore contain arsenic-3, arsenic bound to sulfur, and some arsenic bound to carbon. Arsenic seems mainly to be stored in the cell wall, small amount in the organelles. It's co-localized with oxygen, nitrogen, sulfur, and other metals, but it's also mainly co-localized with sulfur, and we found also these arsenic bound to sulfur species. In hypothesis, it's only in hypothesis we have that arsenic is going into the cell, metabolized, bound to phytokeratins or glutathione, and then exported and stored in the cell wall. More speciation and spatial resolved speciation is needed to confirm, and I have to say, I don't have new data on that yet, because these experiments are running today, in fact today and this weekend at Diamond Synchrotron in Oxford, where we want to see where are the arsenic speciation. We want to do imaging and arsenic speciation at the same time, but hopefully next week we have the data on that. Today I cannot present it to you, sorry. And the beach algae contains a more it's degraded arsenic bound to carbon. Probably the decomposing algae, the arsenic is transformed in more organic forms, maybe due to microbiological processes involved in the algae fouling mechanism. I don't know if I have time for another small project, but I can do it quite quickly. Yeah, together with Jörg Feldmann from Aberdeen University, Eva Krupp, and the team, we were analyzing whale liver also for nanoparticles, mercury nanoparticles with NanoSIMS. And for this, we had to develop a mercury analysis in NanoSIMS, which was not done before. And these are the first NanoSIMS mercury data at all. And it was possible due to our new ion source. So here of a mercury standard, we saw all the mercury isotopes. We could confirm that. In mercury selenium compounds, we see a lot of interferences, apparently from selenium compounds, but we see also the mercury signal just beside the interferences. But what I was talking about, we have a very high mass resolution, and already mass resolution from 3200 was sufficient to separate the interference from the mercury signal. So we could separate these and we could measure on the pure mercury signal. And finally, in the whale liver tissue, here we don't see really cells, but we see tissue, we see particles. We see particles. On these particles is sulfur, selenium, but also we could, for the first time, detect mercury on 2 mercury isotopes here. And also we have iron also inside of these small particles. But we need 18 hours of signal accumulation. So we did a lot of scans, one scan after another, and accumulate all these scans during 18 hours. Here's a second example also. Selenium, again, selenium and mercury. We also detected arsenic inside, and iron, calcium, but also, again, we saw the selenium mercury particles here in the whale liver. Apparently a product of a detoxification process in the whale. So coming to my conclusions here. NanoSIMS is a high resolution technique down to 40 nanometers with a new ion source for subcellular localization of almost all chemical elements in biological cells, but with different sensitivities. The new radiofrequency plasma ion source, oxygen ion source, has been installed on the NanoSIMS for sensitive detection of trace metals. This enables new applications for trace element detection and localization in cell and tissue. This was the dissolution of barium sulfate nanoparticles in the first mercury detection by NanoSIMS. Correlative imaging is also an important point, not to rely only on NanoSIMS images, correlative images with other techniques, and the combination with speciation techniques allows the investigation of biosorption and bioaccumulation processes. For example, arsenic bioaccumulation in brown algae. Many people, of course, I never do something alone. A lot of people are working in collaboration with me or in my team in Pau. And they're from France, from the Bordeaux Imaging Center, from the Frankfurt University, from Orléans in France, Halle University, Aberdeen University, I mentioned that. So all these people were involved here. Also the funding sources here. We got a lot of funding from the French research agency, but also some other funding, and Beamline from Alba and µXRF from the synchrotrons. So thank you for your attention, and I'm happy to listen to your questions. Thank you very much.